This lesson is going to focus on heat energy and the measurements that we use to calculate it. Since most of the chemical reactions that we deal with involve a form of heat, we need to be able to measure this amount of heat that is either absorbed or released by the process. So we already know that heat is difficult to measure directly, but we can measure it indirectly by measuring the heat change of a particular substance. So in order to measure the heat change of a substance, we often use a piece of equipment called a calorimeter. And a calorimeter is often, in our chemistry lab, will just be a styrofoam cup that we use that will have some sort of lid on it. And the idea is that we're trying to make an isolated system as best as possible. We can then measure the heat change of whatever substance we have placed inside of the calorimeter. Now, this is a simple calorimeter that you see in the image here, but at university labs, there's more sophisticated calorimeters that are extremely well insulated. They look like big thermoses, basically, and allow you to have a very, very insulated little area with which to carry out your reaction or your change. And it also allows for a thermometer to be placed inside that will measure the temperature change within the calorimeter. So as we measure the heat change of these processes, we want to be aware of a few important notes. So we have to note or measure the temperature change of our calorimeter in order to know how much energy has been exchanged between our system and our surroundings. The temperature change only will reflect the kinetic energy that has either been gained or lost by our atoms. But we also need to know information about the substance itself. So there's many different types of matter that exist. Some are solids, some are liquids, some are gases, and all of them will exchange heat, or their molecules will speed up or slow down in different ways. So something called the specific heat capacity is a very, very important term to know. And it's also important to know that every substance that exists, every type of matter that exists on Earth has a very specific heat capacity. And this heat capacity is the amount of energy that is required to raise the temperature of 1 gram of that substance by 1 degree C. So again, amount of energy needed to raise the temperature of 1 gram of that substance by 1 degree C. So water is a substance that we typically tend to use in basic chemistry classes that will allow us to know the amount of heat that has been exchanged between system and surroundings. And water's specific heat capacity is actually quite high. It's 4.184 joules. So this is the unit that we use to measure energy per gram degree C. So what this means is that if I had 1 gram of water and I wanted to increase its temperature by 1 degree C, it would require 4.184 joules of energy to do so. So taking into account these measurements and these different values that we need to know, we can calculate the heat of many different substances. We need to know the mass of the substance that has been used. We need to know the specific heat capacity, because again, that is a different amount of energy that is required by every different substance that exists. And then we also need to know how much did the substance change in temperature. And so we use a formula that will allow us to calculate heat, which is lowercase q, equaling the mass of my substance times the specific heat capacity, and that's the symbol for it, times the change in temperature, so delta T. So M is mass, and it is measured in grams. C is specific heat capacity, and it is measured in joules per gram degree C. And then, of course, delta T is your change in temperature, and that is measured in Celsius. We don't use Kelvin here. Kelvin is only used if we're using gases. And here, typically with heat, we don't usually use gases. It's usually solids or liquids that we're dealing with. Heat, of course, so the lowercase q, is also measured in joules. Okay, sometimes we convert it to kilojoules, for significant figure purposes, but most of the time we're talking about it in joules. So what does our Q value actually mean? Well, if you end up with a Q value that is positive, so the value is a positive number, what it's telling us is that our substance or our matter has absorbed energy. If we get a negative Q value, it tells us that the substance has released energy. Okay, so again, remember that some systems are exothermic or endothermic. This is going to help you determine that. Most often when we do calculate lowercase q, this is more reflective of the surroundings. So what has happened here is it's hard for us to measure the temperature change of a system itself. Usually what we need to measure the temperature change of is the surroundings, but we know that the amount of energy that flows between system and surroundings should be the same. So when we are measuring Q, typically we are measuring the surroundings, and it's giving us an indication of whether the system released or absorbed energy. So let's do a very simple calculation using our basic heat formula. And it says 200 grams of water in a calorimeter has its temperature raised by 3 degrees C due to an exothermic chemical reaction. How much heat was transferred? So we're going to set up our formula of Q equaling mc delta T. We are measuring 200 grams of water. So we're going to place that in. C is our specific heat capacity of the substance. Well, the substance is water. And you need to know the value for the specific heat capacity of water. So 4.184 joules per gram degree C. Okay, and again, I don't have 1 gram, I have 200. So we're going to account for that. And I also didn't increase the temperature by 1 degree C. I increased the temperature by 3 degrees C. So we're accounting for all of these good changes that have happened as there has been a heat exchange happening. When we are doing these calculations, keep in mind significant figures. So we're multiplying here. We want to round to the fewest number of significant figures. And also keep in mind that there are different specific heat capacity values that exist out there. You are expected to know waters because it's so common. Anything else will be found in your data booklet. When we multiply this through, we get 2510.4 joules, okay, because the grams are going to cancel out. There's grams in the numerator, there's grams in the denominator. There's Celsius in the numerator, there's Celsius in the denominator, right? Remember, there's a divided sign there. So we're left with joules. I need 2 significant figures. You can either put this into scientific notation and report it that way, or what I would do is I would divide that out by 1,000, and I would report my value as 2.5 kilojoules. Okay, and you don't have to do that. You can leave it in scientific. I just don't care for it. So if I can switch it to a different unit, I'll do that. Here's another example that we can try. So it says here a 1 kilogram sample of water whose temperature was 50 degrees C lost 33,000 joules of heat over a 5-minute period. What was the temperature of the water at the end of the 5 minutes? Okay, so we're going to be looking for the final temperature here. It's lost heat. So we'll recall a couple slides back that if we've lost heat, that would be a negative value. So we're going to set this up, and we now know my Q value. So we're not going to be solving for that. And we know that it lost 33,000 joules over time. So we need to put a negative sign in there. My mass of water is 1 kilogram. I need a unit of grams because my specific heat capacity of water is in a gram unit, joules per gram degree C. And I'm going to have to fiddle around with the delta T. I need to figure out the final temperature. So I'm actually just going to leave it right now as delta T and solve for that. So I'm going to rearrange this and I'm going to solve for delta T. I'll end up with negative 33,000 joules. In the numerator, I'm going to divide by 1,000 times 4.184, which is 4184. And what cancels out? I end up with joules per degree C because my grams are going to cancel out. When I do this math, I end up with a value of negative 7.887, carry it that far, degrees C. And that's not my final answer because that is just the change in temperature that happened. So we know that it lost heat, and we know that the temperature had to go down over time. So let's just sub in what we know. We know that T final minus T initial is going to be equal to negative 7.887 degrees C. I'm solving for final temperature. My initial was 50 degrees C. That's equal to negative 7.887 degrees C. I'm going to bring this up here. So my final temperature is going to be equal to negative 7.887. And when I bring my minus 50 over to the other side, I'm adding it. And I'm now adding my values here. So what I want to do is be aware of the significant figure rule of addition. And so I need to round to 1 decimal place. And when I subtract or add these values together, I end up with a value of 42.1 degrees C as my final temperature. Here's another good example that is an application of our MC delta T formula. So what they're doing here is they're taking a piece of metal with a mass of 105 grams, and it's hot, it's 100 degrees C, and they're going to place it in a different substance. They're placing it in water to cool down. And it says that the water temperature increased from 22.8 to 39.2. This is important because this right here is my final temperature. And at that temperature, both substances are now 39.2 degrees C. We know that heat flows from the hotter substance to the colder substance. And we can tell the metal was hotter, the water was colder, and the metal's heat flew into the water until they stabilized at the same temperature. So we know that that TF is the same for water and the metal. This is very important that we recognize that. And then they're asking us what is the specific heat capacity of the metal. So we can solve for this. What we know is that the second law of thermodynamics states that the heat of our hot substance is going to be transferred into the cold substance, and that amount is going to be equal. Whatever amount of heat that the hot substance lost is going to go into the cold. The hot is going to go down in temperature. It's going to lose energy, so we have to put a negative sign in front of it. Now, Q is equal to MC delta T. So we're going to be writing this out on both sides. And it's our job just to know, who's the hotter substance, who's the colder. Well, the metal is hotter and the water was colder. It was at 22.8. So let's sub in what we know. We know that the mass of the metal was 105 grams. We do not know the specific heat capacity. This is what they're asking us to solve for, but we know the delta T. So delta T is always final minus initial. Well, the final is 39.2. Remember, they don't tell you that, but you know that because if the water goes up to 39.2, the metal has come down to 39.2, and now there's no more heat exchange. And we're going to subtract that off of the initial, which was 100 degrees C. Now we go over to the cold side. So the cold side is our water. The mass of our water is 175 grams. The specific heat capacity of water, notice they don't give it to you because they know you know it, 4.184 joules per gram degree C. And then we need to do the delta T. So remember, it's final minus initial. It's 39.2. And we're going to subtract off the initial, which was 22.8. So let's clean this up. Let's, subtract where we can, multiply where we can. And we'll do this in baby steps for you. So we're going to do negative 105 grams times C, delta T, let's do it. When we subtract those off, we get negative 60.8, and that makes sense. Temperature is going down. And then on the other side, let's do this delta T right here. When we subtract that off, we get 16.4 degrees C. And now let's multiply everything together. When I multiply everything together, I am getting 12008.08 on that side. So that'll be joules. Let's multiply my 105 by 60.8, and that gives me a value, those negatives will cancel, of 6384 C equaling 12008.08 joules. Okay, sorry, so this is now, actually we should keep track of our units here. This is grams degrees C right there. So we're going to solve for C, and we're going to take 12008.08 joules, and we're going to divide by 6384 grams degrees C. Pardon me. And we're going to divide this out, and now we have to round two significant figures. So while I'm looking at all of this, right, I have three significant figures, seems to be pretty much everywhere. There's 3 there, there's 3 there. This is a constant. We don't use constants in sig figs. When I subtract this off, I was getting 3 sig figs, 3 sig figs. So when I do this math, I'm getting a specific heat capacity of 1.88, and there are my units, right? Joules per gram degrees C, which is the unit you're supposed to have for a specific heat capacity.